Okay, so in this lesson, we're going to talk about polynomial functions, the end behavior of these polynomial functions, and the leading coefficient test. And the leading coefficient test will help you to identify the end behavior of these polynomial functions. Now, you've graphed polynomial functions in a previous lesson. Remember when you graphed quadratic functions? So when you graph quadratic functions, all right, remember these quadratic functions were polynomial functions. So these are considered polynomial functions. All right, now before we kind of give a definition of what a polynomial function looks like, just remember what a quadratic function looks like. So a quadratic function has this form. It's f of x equal ax squared plus bx plus c. And remember, when you graphed these quadratic functions, remember these quadratic functions are polynomial functions, but when you graph these quadratic functions, remember the graph is a parabola. For a quadratic function, the graph is a parabola, and the parabola either went up or it went down. Okay? So you'll notice that when you graph these, you either got a graph that looked like this or a graph that looked like this. Now, remember, these are polynomial functions. They're considered polynomial functions. Now, the end behavior, what we mean by end behavior is this. The graphs on the outside. So this part here, that's what we consider end behavior. All right, what happens on the outside of the graph. So this would be considered end behavior. Okay, so as we go through this, you're going to see what we mean by end behavior. So for example, if we look at a polynomial function that's not quadratic, you could get a graph that look like this. All right, so just bear with me for a moment. So it could look like this. Okay, oops, sorry. All right, so it could look like this. So you had this graph. Notice how I'm drawing this. So these graphs here, the polynomial functions, the graphs are smooth, continuous curves. Smooth curves, they're all curves, and it's continuous. What I mean by end behavior for this one, though, is this. What happens over here, that's what happens. Okay, that's what we mean by end behavior. So end behavior. What happens on the outside of the graphs, on the ends of the graphs. Okay? Now, let's go back to the quadratic functions that you've graphed. So notice that the end behavior of this quadratic function, of this polynomial function, the end behavior, they're both rising. So on the left side, your graph is rising. On the right side, your graph is rising. Over here, the end behavior, they're both falling. So fall on the left, fall on the right. Rise on the left, rise on the right. Fall on the left, fall on the right. So if I look at the bottom, the graph that we just did a while ago, this would be on the left side. So this is the left side, this is right side. On the left side, your graph is falling. On the right side, your graph is rising. Fall on the left, rise on the right. Rise on the left, rise on the right, fall on the left, fall on the right. So that terminology is going to be important. So that's what we mean by end behavior. What's happening on the ends of the polynomial functions. Okay? All right, now let's go back to the quadratic function and talk about, if you recall, what made this parabola rise and what made this parabola fall. So let's kind of talk about that, and that's going to help us with these polynomial functions. Okay, now let's look at this again. All right, so I'm gonna draw, or not draw, but I'm gonna write the quadratic function ax squared plus bx plus c. Now remember, when we talked about whether the quadratic function went up or went down, okay? So whether it goes up or goes down, remember the coefficient of x squared, a determined that. So remember we talked about the leading term, the leading coefficient. So the leading coefficient determined if the quadratic function, if the graph of the quadratic function went up or down. Okay? So for example, if you look at this one, f of x, and this was on one of your tests, but if f of x equal negative 2x squared plus 3x plus 4, let's say, and without graphing this, you could tell me, and remember in the previous lesson, this was on your last test, but you could tell me whether this parabola opened up or down. All right, so the parabola, remember this quadratic function, it's a polynomial function, and it's a quadratic function, so the graph is a parabola since it's quadratic. The parabola opened down because the leading coefficient here was negative 2, was negative. So since a is negative, meaning this, okay, negative 2, since a is negative, remember that's called the leading coefficient. Leading coefficient. Since a is negative, the parabola, the graph, opens down. All right, so it looks something like this. So if we talk about the end behavior, we'll say that in terms of the end behavior, we would say that the graph falls on both ends. Falls on both ends. Okay? All right, now, number 2, let's suppose I had this. G of x equal 4x minus 2 plus 7x squared. Okay, 4x minus 2 plus 7x squared. Now, you need to be a little bit careful with this one because what some students seem to think, and we've had the discussion before, what some students seem to think is that the term listed first is the leading term. Okay? So you got to be careful when we talk about the leading term, we're talking about the leading term when you put this in descending order. So you always want to make sure that the largest degree term, remember we talked about degrees before, so this term right here has the largest degree. So you want to make sure that it's in descending order. You want to make sure that it's listed first. Okay, so you have to rewrite this as 7x squared plus 4x minus 2. So you've got to make sure it's in descending order. Okay, now, descending order. Now this is my leading term. So your leading term is the term, we consider the leading term to be the term with the largest degree. So that's the term that has degree 2. Remember, this has degree 1, and this constant has degree 0. Now this leading term, the leading coefficient, is 7. Leading coefficient is 7. So A here is 7. So since this is positive, all right, so since this is positive, and when I say this, I mean the leading coefficient, since that's positive, the graph, in terms of leading behavior, remember the graph does this, so the graph rises on both ends. The graph rises on both ends. Okay? All right, now, let's give a formal definition, though, of a polynomial function. Now, this definition I'm about to write it looks extremely complicated. Most students, when they first see this, most college algebra students, when they first see this, they don't understand what it's saying. All right, but just remember, a polynomial function, a quadratic function is a polynomial function, so keep that in your mind, what it looks like. Okay. All right, so let's go to a formal definition of a polynomial function. All right, so let's see. All right, so let's talk about polynomial functions. So here's the definition of a polynomial function. Definition of polynomial function. All right, so it's defined by, all right, now we'll go look. This is what blows some students' minds. All right, so listen carefully. So you have, and we're talking about the variable x here. So we have some x raised to some large power, and this exponent is the largest exponent, so that's going to be the largest degree term. So that's my leading term. Okay, this number right here is called the coefficient. So this coefficient we're going to call right here a sub n, and this n corresponds to this n. Then we have the next one. Next one will be n minus 1, and then this coefficient is a coefficient of the term that has exponent n minus 1. So hence a sub n minus 1. The next one would be, if you wanted to do the next one would be plus, x to n minus 2, raised to n minus 2, and then the coefficient would be a sub n minus 2. So the subscript here corresponds to the exponent here. And then plus a1, sorry, that should be a2. a2x squared plus a1x plus your constant a sub 0. So remember, this right here, if I cover everything else, that's that's your leading one, then that, remember, is quadratic. So that will be quadratic. Then the next one will be cubic, x cubed, and so on. Okay? So notice your exponent's 2, so x squared, the coefficient of x, of the term x squared is a sub 2. The coefficient of x term is a sub 1, and then your constant is a sub 0. All right, so it is complicated to look at, but don't let it throw you off. All right, now, in order for it to be polynomial, though, in order to be polynomial, your exponents have to be non-negative integers. So your exponents must be integers, and they cannot be negative. Okay? So they must be non-negative. All right, so for example, let me go ahead and just give you some examples of what I mean by this. And also, your coefficients, though, can be any real number. So the coefficients can be any real number as long as if this is your leading term, then your coefficient here cannot be 0. Okay? So your leading term coefficient cannot be 0. All right, so here's some examples. So examples of polynomial functions. Okay, so examples of polynomial functions. Number 1 would be something like f of x equal 5x squared minus 3x plus 2. All right, so notice that all of the exponents are integers, the exponent of the variables. This exponent is a positive 2, this exponent is a positive 1, you have a constant. You don't always have a constant, though. You don't have to have a constant. But you do have to have a polynomial where your largest exponent is 1 or above. Okay. Now, in a little while, though, remember we talked about smooth curves, so we need this to be greater than or equal to 2. So we're going to need n to be greater than or equal to 2. Okay. All right. And then notice that the coefficients of your terms are any real number. Number 2, g of x equal 2/3 x to the 5th minus 3x squared plus 7x. All right, so here's another example of a polynomial function. The leading term, the largest, I have the leading term listed first. That's the one with the largest degree. So it's 5. This degree, this exponent is 2. This exponent is 1. Notice I don't have a constant. You don't have to have a constant. And all the coefficients are real numbers. Okay. Number 3, h of x equal negative 3x plus 8x to the 5th plus 7x to the 6th plus 2. All right, so this is still a polynomial function. It is not in descending order. All right, so don't consider this a leading term. When we put in descending order, our leading term is going to be this right here. Okay, so but notice that all the exponents are integers, positive whole numbers. Okay, the coefficients are all real numbers. All right, now these are not examples. Not examples. Okay, for example number 1, g of x equal 4x to the 5th power minus 2x cubed plus 7x to the 2/3 plus 5. So that's not an example of a polynomial function. And the reason it's not is because you look at these 4 terms. This term here, this is a term that makes this not a polynomial function. If that term wasn't here, and I just looked at those 3 terms, then it would be polynomial. But can you think about what makes this not a polynomial function? What about this term makes this not a polynomial function? It's still a function, but why is it not a polynomial function? All right, if you said the exponent, you're correct. Remember, this exponent right here, this is not a whole number. It's not a positive integer. Okay? It's not a positive integer. It's a fraction. See, 2/3. All right, so that's why it's not. All right, now keep in mind though that you could also have it written like this. You can have a function that's not polynomial that looks like this. Let's say 3x squared plus 5 square root of x minus 2. All right, now the issue is this one, because remember the square root of x means the same thing as 5x to the 1/2 power. All right, the square root of x means 5x to the 1/2 power. So again, that brings us back to this. This right here is not a whole number. Okay? Number 3, f of x equal 2x cubed minus plus 7 divided by x squared minus 3x. All right, so again, the issue here, the thing that makes this not a polynomial function is this right here. And if you remember 7 divided by x squared, 7 divided by x squared means this. Means I can write this as 7x to the negative 2nd power. So the issue is this right here. So my exponent is not a whole number. So in other words, it's not a positive integer. Okay? All right, so those are examples of polynomial functions, and those are examples of functions that are not polynomial functions. All right, what we're going to be interested in, though, is these polynomial functions. What are the end behaviors? What happens without graphing? What happens to the ends of these polynomial functions? Okay. All right, now. Okay, so now we're going to talk about what the graphs look like. All right, so we alluded to this a while ago. So when we graph the parabolas, so remember the quadratic functions. So when I graphed it, remember it's a smooth curve. It either did this or it did this. Remember that? Okay, so these are smooth curves. Now by smooth, I mean this. I mean when I say smooth, what I mean is that there are no sharp turns. No sharp turns. So in other words, when I graphed this, I didn't do anything that looked like this. Okay, see there right here, I did a sharp turn. Okay, it's not smooth like this is. This is sharp. It's kind of like this. Right? So these are sharp turns. So sharp turn. There's no smooth. It's kind of like driving in a curve. All right, so think about driving in a curve. So here you're driving in a curve. So it's very smooth driving. Driving in a curve, you're smoothly driving. Here you're driving in a curve, and then all of a sudden you're making a sharp turn. You're driving, and all of a sudden you're making a sharp turn. Okay, so that's what I mean by smooth and not smooth. All right, so the graphs of polynomial functions are going to be smooth curves. They're not going to look like these. Okay. All right. The other thing is that the graphs of polynomial functions, are continuous. So they're smooth and continuous. All right. So what I mean by continuous is this. All right, continuous. So when I drew the parabola nowhere did I lift my pencil. See, I did not lift my pencil at all. I just kept drawing. I just kept drawing. Okay. Remember a while ago you graphed piecewise functions. So when you graph piecewise functions, I want you to notice something. When you graph piecewise functions, you could have graphed something that looked like this, and then all of a sudden you could have graphed something else that looked like this. And so notice that when I draw this part here, this piece, I have to jump over here to get to that piece. So this would be discontinuous. So this is discontinuous. All right, discontinuous. So it's not continuous like these are. There's a jump. There's a gap. Think of a gap. Okay? There's a gap in the graph. All right, so discontinuous. So that should have been an open circle here. Remember, it's still a function. So remember, and then you graph, when we talked about this, you graph something that look like this, let's say. And then remember, most of the time it was a line that you drew. Okay, but still, that is not continuous. This is not continuous. All right. So basically what happens then is this. So let's kind of review what we just did for a moment. All right, so the graphs of polynomial functions of degree, and we're talking about quadratic function or above, degree 2 or higher, are smooth and continuous. So they're smooth and continuous. So remember, by smooth, I mean that the graphs contain only rounded curves with no sharp ends. Okay? Continuous means that the graphs have no breaks, so no gaps in the graph, and can be drawn without lifting your pencil. All right? Okay, now, polynomial graphs are going to look like this. So graphs of polynomial functions will look like this. So you may have something, this is your xy axis, you may have something that looks like this. Notice how I'm drawing this. Okay? So all of these are smooth curves, and notice there are no gaps. Okay? Here's just one example. So notice the end behavior. I still want you to keep in mind the end behavior. So the end behavior, on the left side, your graph's falling. On the right side, your graph is rising. That's going to be important. If we look at this one, you have something, let's say, that looks like this. Notice I'm drawing smooth curves, and it's continuous. So no gaps. Notice on the end behaviors. On the left side, it's rising. On the right side, it's rising. So it's rising on both ends. Okay. You could have something look like this, let's say. So notice smooth curves. It's continuous. There are no gaps. Notice the end behavior. End behavior on the left side, it rises. On the right side, it falls. Okay? Now, a couple of things using these, couple of things I need to tell you. So we're going to use remember we talked about infinity before. You know what infinity means. In terms of domain, notice that the domain here would be from negative infinity all the way to infinity. Okay? So that makes sense to you. And the range is also from negative infinity to infinity. Okay, so notice that in all of these, well, I got to be careful. In all of these, the domain, though, is all real numbers. So domain, negative infinity to infinity. The range, though, is not always going to be negative infinity to infinity. Here, the range would be from this low point all the way to infinity. Here, the range is all real numbers because the arrows are pointing in opposite directions. Okay? But for polynomial functions, the domain is all real numbers. So here's what I want you to think about. All right, so as x goes to infinity, so as x goes to infinity, so as x gets bigger and bigger and bigger, what's happening to these y values? All right, so your y values are doing what? Well, your y values are increasing. They're going to infinity. So y goes to infinity. For this graph, that's what's happening. So as x goes to infinity, as x gets bigger and bigger and bigger, your y values goes to infinity. All right, let's talk about this side now. So x goes to negative infinity. What are your y values going to? Well, my y values are doing what here? Well, your y values are decreasing. They're getting smaller and smaller and smaller and smaller. So they're getting closer to negative infinity. Oops. Okay, negative infinity. All right. It's not that difficult to understand. Let's do another one. Let's do this one. So as x goes to infinity, as x gets bigger and bigger and bigger, what's happened to your y values? Well, your y values are getting bigger. So y is going to infinity. On this side, as x goes to negative infinity, what are your y values going to? So as x goes to negative infinity, your y values are also getting bigger and bigger and bigger and bigger. So they're going to infinity. All right, let's talk about this right here. As x goes to infinity, as we get bigger and bigger and bigger in terms of x, what's your y values going to? Well, my y values on this end, we're talking about these are all about end behaviors. So on this end, your y values are getting smaller and smaller and smaller. So y approaches negative infinity. Okay, let's talk about going this side. As x goes to negative infinity, y approaches, so as x goes to negative infinity, on this end behavior, y approaches positive infinity. Okay? All right, so as we go through this, we're gonna talk about these ideas again. Okay? All right, now. Okay, so now you want to ask yourself this. What part of the polynomial function determines the end behavior? What part of the polynomial function determines the end behavior? What part of the polynomial function determines the end behavior? Well, remember we talked about that at the beginning of the lesson. So if I go back to, let's see if I can find it real quick. If I go back to the quadratic functions we drew earlier, this right here. All right, so the leading coefficient determines the end behavior. Remember that? The leading coefficient determines the end behavior. So if the leading coefficient is negative, now this is quadratic right here, so you got to be careful. So if the leading coefficient is negative for this quadratic function, the end behavior went down on both ends. Over here, for this quadratic function, the leading coefficient was positive, so the end behavior on both ends, it rose. The end behavior rises. Okay? But that was only true for quadratic function in terms of falling or rising. But the leading coefficient is what we look at. So we always look at the leading coefficient. Okay? All right, so let's talk about the leading coefficient test, something called the leading coefficient test. Leading coefficient test. So the behavior of a graph of a function to the far left or the far right, meaning this, far left or far right, left end, right end, far left, far right, left end, right end, far left, far right, left end, right end. I don't care what happens here. I'm just interested in what happens on the outsides, on the ends of the graph. I don't care what happens here. I just want to know what happens on the ends of the graph. Does the graph go up or does the graph go down? Does the graph go up or the graph goes down? Does the graph go up or does the graph go down? Does the graph go up or the graph goes down? That's what I'm interested in. And that's what the leading coefficient test will help you to determine whether the graph goes up or down on the ends. That's all it does. Okay? It doesn't tell you anything else about what happens between them. Doesn't say anything else about what happens between them. Okay, so that's what we mean by far right, far left. So that's called your end behavior. Although the graph of a polynomial function may have intervals where it's increasing or decreasing, so notice that when we graph these, notice it's increasing, decreasing, increasing, decreasing, increasing. So although the graphs of polynomial functions have intervals where it's increasing and decreasing, it will eventually rise or eventually fall. Okay, it will eventually go up. It will eventually go up or eventually go down. It will eventually go up or it will eventually go down on the ends of the graph. Okay, so it will eventually rise or fall without bound as it moves to the far left or the far right. So in other words, you're increasing, all of a sudden, you're decreasing, all of a sudden you're increasing. You're decreasing, and then all of a sudden you're increasing forever. Notice I use the word forever. Over here, now remember we're talking about going to the left here, okay? So as I go to the left, notice your graph falls forever. It falls forever. It rises forever. It rises forever. It rises forever. So as x goes to positive infinity, your graph rises. As x goes to negative infinity, your graph rises. As x goes to positive infinity, your graph rises. Your y values increase. As x goes to negative infinity, notice this right here, your y values decrease forever. Okay? All right, now. Okay, so now what this is this. So let's just kind of summarize what we just did. See how this, you can't see it very well, but this is y equals negative x squared minus 2x plus 8. So with this polynomial function, the leading coefficient is negative. So that means that on the ends, the end behavior, notice that the end behavior is falling on both sides. Okay? Over here, this is y equals 3x squared plus 5x minus 2. Notice that this coefficient is positive, so the end behavior, your graphs are rising on both ends. All right, so notice that as x goes to infinity, what are your y values doing? Your y values are going to negative infinity. As x goes to negative infinity, your y values goes to negative infinity as well, because they're, notice, falling on both ends. That's what that means. Over here, as y goes to, as x goes to positive infinity, what are your y values doing? Your y values are increasing. So it's going to infinity. As x goes to negative infinity, what are your y values doing? Your y values are increasing. All right? Now, I want you to notice something. When we talked about the quadratic function, the degree was 2, right? That's an even number. So even. All right? So the degree was even. So it turns out that if the degree is even, You're going to see this in a little while. If the degree is even, your graph on the ends will either be pointing down or they will be pointing up. If the degree is even, if the largest exponent is even, the end behavior will either be pointing down or they will be pointing up. Regardless if this is x squared, x to the 4th, x to the 6th, x to the 8th, x to the 10th, x to the 12th, the end behavior will either be pointing down or be pointing up. Now I'm going to ask you again, what determines whether the end behavior is goes down or the end behavior goes up? The leading coefficient. If the leading coefficient is negative and your exponent's even, it goes down. If the leading coefficient is positive and your exponent is even, the end behavior will be going up. Okay? So the issue, so even is easy. Even, if the leading coefficient is even, your graph's going to go down. If the leading coefficient is negative, your graph will rise on both ends if the leading coefficient is positive. Let's talk about odd. It's the odd ones that cause a little bit of issue. So here's what I want you to do. To help you with that, to help you with determining what happens if the leading, if the degree of the polynomial is odd, if the largest exponent is odd. To help you with that, let's look at a simple case. All right, let's go ahead and graph. Let's go ahead and graph this. Let's graph this. So let's graph. Let me go ahead and remove all this. Let's graph y equal x cubed. All right, y equal x cubed. All right, y equal x cubed. So notice the degree here is odd. So we're looking at an odd degree. And the leading coefficient is positive. So the leading coefficient is positive. All right. So if I use a t-table, let's see what happens. So if x is 0, 0 cubed is 0. So I plot the point 0, 0. That's just right here. If x is 2, I get 2 cubed, which is 8. So I plot the point 2, 8, which is here. If x is 1, I get 1 cubed, which is 1. So I plot the point 1, 1, which is here. If x is, and I can't go any further in terms of using integers, because if x is 3, 3 cubed is 27, and I don't have enough room. But I do know it's way up here, right? So that part of the graph looks like this. That looks like this. And let's go about on this side. If x is -1, I get -1 cubed, which is -1. So -1 is right here. If x is -2, I get -2 cubed, which is -8. -2 cubed is -8. And so again, I have this. Okay? Now, notice what happens. Look at the end behavior. So as x goes to infinity, what happened to your y values? Your y values are doing what? Your y values are increasing. Okay? So in other words, on the right-hand side, as x gets big, on the right-hand side, your graph rises. As x goes to negative infinity, so as x gets smaller and smaller and smaller, what happens to the end behavior here? Well, the end behavior falls. Notice that my y value is getting smaller and smaller and smaller. Okay? So that means that on this side, on the left side, it falls. All right? So the end behavior falls on the left, rises on the right. Okay, so falls on the left, rises on the right. Now that's true if the degree is odd, if n is odd, That's true if n is odd. Okay, true if n is odd. And a sub n is positive. Okay, so the leading coefficient is positive. So if your degree is odd and your leading coefficient is positive, they'll fall on the left, rise on the right. Okay, now let's look at this one now. Let's look at negative x cubed. Y equal negative x cubed now. Okay, y equal negative x cubed. All right, so let's plot some points. Use the t-table. If x is 0, 0 cubed is 0. The opposite of 0 is still 0. Okay, so I plot the point 0, 0. If x is 1, I get number. You got to be careful. The only thing being cubed is x, not negative x. So if x is 1, 1 cubed is 1. The opposite of 1 is negative 1. So 1, negative 1 is right here. Right here. If x is 2, I get this right here. So 2 cubed is 8. The opposite of 8 is negative 8. So I get 2, negative 8, which is right here. So notice on this side, it does this. All right, if I go on the other side, if x is negative 1, I get the opposite of negative 1 cubed. Well, negative 1 cubed is negative 1, and the opposite of a negative 1 is a positive 1. So I get negative 1, positive 1, which is right here. If x is negative 2, I get the opposite of a negative 2 cubed. A negative 2 cubed is a negative 8, and the opposite of a negative 8 is a positive 8. And so I get this. So notice on this side what it's doing. Okay? So if let me do this first. So you see now it does this. So now on the right side, on your right side, your graph falls. On the left side, your graph rises. Whereas over here, we did this one, on the right side, it rises. On the left side, it falls. Okay, now remember what made this rise and this fall here? Well, first of all, your leading exponent, your degree is odd. If the degree is odd, notice if the degree is odd, on one side the graph rises, on the other side the graph falls. If the degree is odd, on one side the graph rises, on the other side the graph falls. If the degree is odd, on one side the graph rises, on one side the graph falls. Rises, falls. If the degree is even, remember the degree is even, either they both fall or they both rise. Okay? So that's easy to remember for even. Think of your quadratic function. For odd, think of x cubed. Always have that in your mind for odd, x cubed. So if it's negative, if the leading coefficient is negative and your degree is odd, let's talk about this. Remember how we did here? So if the degree is odd and the leading coefficient is positive, on the right it rises, on the left it falls. That's what this is saying. Over here, what is the degree? Is the degree odd or even? Well, the degree is odd, so n is odd. Okay, n is odd. So now let's talk about the n behavior. All right, let's talk about the n behavior. So the degree is odd. All right, degree is odd on the, so degree is odd, and a sub n is negative. Okay, a sub n is negative. Remember that was negative here. The leading coefficient is negative. That's when by a sub n. Leading coefficient is negative. Then what happens is that on the right side it falls, on the left side it rises. That's how it's going to look. On the right side it falls, on the left side it rises. So left side rises, right side falls. Okay? Left side rises, right side, false. Okay, now, this table should help you to understand this a little bit better. All right, so remember our leading term right here, a sub n, x to the n power. So if n is even, remember it rises or it falls. That's easy. Rises or it falls. If n is odd, on one side it rises, on the other side it falls. Okay? On one side it rises, on the other side it falls. Okay? If they're both pointing the same direction, then it's what kind of degree? It's even. If on the ends they're in opposite directions, then it's odd. Okay? All right, now, if the leading coefficient is positive, let's talk about even. If the leading coefficient is positive, it's going to rise. If the leading coefficient is negative, it falls. That's the easy kind right here. Let's talk about this one now. For that one, remember, always think about x cubed. For x cubed, it does this. Okay? For negative x cubed, it does this. All right, so again, if you look at our graph that we did a while ago. So for positive x cubed, positive 1x cubed, this is what it looked like. So on the right, it rises. On the left, it falls. For negative x cubed, on the right, it falls. On the left, it rises. All right, so let's look at this. So we're dealing with odd, so notice the opposite in behaviors. One's falling, one's rising. Okay? Now, if n is positive, if the leading coefficient is positive, that's what this is right here. Rises on the right, falls on the left. If the leading coefficient is negative, like this is right here, see how the end behaviors? Look at the end behaviors. Right here, right here, right here, right here. So the end behaviors rises on the left, falls on the right. Okay? All right, so if you look at this example, see how this is f of x equal negative x to the fourth plus 7x cubed minus 14x minus 9. So I just want you to tell me something about the end behavior. Well, first of all, it's even. So you know that your end behavior will be pointing in the same direction. It will be pointing in the same direction. It will do this, or it will do this. Okay? So the question to you becomes this. Which one is it doing? Is it rising or is it falling? Well, you got to look at your leading coefficient now. So this is what you use to determine whether it rises or whether it falls. Okay? Since it's even. The leading coefficient, since it's negative, tells you that it's going to fall. So it falls on both sides. So it just says it's down on both ends. Okay? Over here, g of x equal 5x to the fifth plus 2x cubed minus 14x squared plus 6. Okay, first of all, make sure it's in descending order. So then this is going to be your leading term right here. This is odd. So remember, if it's odd, it will either do this. Okay, we'll do one of these. It does this if your coefficient is positive. It does this if your coefficient is negative. So look at your leading coefficient. Leading coefficient is positive. So you have to do this. So that's what we say down, falls on the left, rises on the right. Falls on the left, rises on the right. Okay? All right, now let's use this to help us with these now. All right, so this is what you got to be able to do at this point. At this point, okay, so now we're at the point where you'll see the kind of problems that would be on your test. All right, so there are 6 examples here. All right, 6 examples, and if you can do these, you should be fine. All right, so you use the leading coefficient test to determine the end behavior of the function. All right, number 1. So first of all, make sure it's in descending order. Okay, make sure you actually have your leading term first, so you don't make a mistake. All right, first of all, is this in descending order? Yes. So here's my leading term. First thing you want to do is look at the exponent. Your leading, your degree, the degree of this polynomial function is 2. That's even. Okay, so if it's even, either it rises or it falls. Either rise on both ends, falls on both ends. Remember that? Look at the coefficient. This positive. If it's positive, then it means that it's going to rise. So it rises on both ends. Okay? So do something like this. Okay, number 2. Is it in descending order? The answer is yes. The degree is 5. That's odd. All right, so if it's odd, on the ends, it will be in opposite directions. Either it will rise on the left, fall on the right, or rise on the right, or fall on the left. I'll do one of those. Okay? That's where the leading coefficient comes in now. So since the leading coefficient is negative, he'll do this one. Okay? If you cannot remember which one it does, think of negative x cubed. Negative x cubed. And so when you graph negative x cubed, that's the one that looked like this. All right, so look at the end behavior. Rise on the left, fall on the right. Okay? So this will, now that's not the graph of this, but you can use that idea. So it's going to rise on the left, fall on the right. Okay? All right, next one. Is it in descending order? The answer is yes. So the degree here is even. So it's either going to rise or it's going to fall. So since the leading coefficient is positive, it's going to rise on both ends. Okay? The next one. Number 4. Is the polynomial function in descending order? No. So let's put in descending order. So we're going to have 7x cubed minus 2x squared plus 5x plus 3. Now look at the leading coefficient and the exponent. So the degree of this polynomial is 3, so that's odd. The leading coefficient is positive, so if it's odd, remember, think of x cubed. If it's odd, if it's x cubed, it looks like this. So it rises on the right, falls on the left. So since this is odd and the leading coefficient is positive, you will say fall on the left, rise on the right. Okay. Number 5, is this in descending order? No, let's put in descending order. So this would be 6x to the 8th plus 3x cubed minus 7x squared minus 2. All right, so you're not graphing any of this. You're just looking at what on the outside, what does it do? Okay. So the degree of the polynomial tells you that. So the degree of this polynomial is 8. That's even. This is positive 6. So the leading coefficient is positive, so that means that it's going to rise on both ends. So rise on both ends. Okay? Let's go ahead and make this, I'm going to change this to minus right here. All right, so is this in descending order? No. So I'm going to put in descending order. I get negative 5x to the 4th minus 2x cubed plus 3x minus 2. Okay? So the degree is even. The leading coefficient is negative. Okay? So that means that it's going to fall on both ends. So it falls on both ends. All right? And so that's all you do. That's all the leading coefficient test does. It just tells you what happens on the ends. Doesn't tell you anything. Does not tell you anything. Just tells you what happens at the ends. Does not tell you anything about what happens between them. Okay, doesn't tell you anything about what happens here. Just tells you what happens on the ends. All right. Okay, so that's going to take care of this lesson. And so in your test, your problems will look like this.